In this video, I am going to introduce DSI Studio Cloud, a cloud computing environment for tractography analysis. Before I show how to use it, you may wonder, why do we need cloud computing and what are the benefits? Here are some points. First, diffusion MRI data are usually quite huge. Some scans data could be up to the size of gigabytes. However, the output of the pipeline such as the tractography or connectivity matrix are usually much smaller. Using cloud computing, you can keep data transfer on the cloud and save a lot of data transferring time. There is no need to store data locally just for processing. The pre-processing and analyses could be done on the cloud computers, and we only need to download the final results. Second, the computing resource available on cloud computing is much cheaper and more powerful than regular laptop or desktop. DSI Studio Cloud uses computing resources offered by GitHub Action. GitHub Action offers 20 concurrent jobs with 2 CPU core each. That is equivalent to a 40-core CPU workstation. The computation power is much stronger than most laptops or desktops. Most importantly, getting an GitHub account is free. For public repository, you have unlimited and free computing resources. Third, DSI Studio Cloud is portable across platform and hardware, and we can initiate the computation from any devices. You don't even need a computer to run DSI Studio Cloud. A cell phone is enough for tractography analysis. There are some limitations. The free resource on GitHub has restrictions on the cloud storage. Currently, DSI Studio Cloud is only good for small to mid-sized projects that have less than 200 scans. There are also requirements to run DSI Studio Cloud. You would need to have a GitHub account. It is free, unless you would like to use some paid resources. Currently DSI Studio Cloud only supports data stored on OpenNeuro. OpenNeuro is a free and open platform for sharing BIDS-compliant data. However, you cannot store private data on it. The raw data and the analysis results can be downloaded by anyone from the Internet. In the future versions, DSI Studio Cloud may support other data storage platforms, but currently OpenNeuro is the only option. Now let's work out some diffusion MRI data using DSI Studio Cloud. If you want, you may follow the steps on your laptop or even on a cell phone. First, open a web browser and then go to the GitHub website at github.com. Sign up to get a free account or sign in your existing account. Then in the search box, enter DSI Studio Cloud to find its repository. It should be listed under an account named Frank Yer. Click on the link and go to the DSI Studio Cloud repository. In the front page, there is a documentation about how to use DSI Studio Cloud, including the available pipelines, parameters, and steps to start the analysis. On the right, the output of the analysis results will be stored under the release section. We will check this out later after we run a sample dataset. The GitHub action can be viewed and initiated at the Action tab. However, only the account owner can run the action, and you will not be able to run it under my account. To use it, you will need to copy this repository to your account by clicking on the Fork button on the right upper corner. Now, click on the Fork button, and then you will have a copy of DSI Studio Cloud in your repository list. To find it, check out your repository list to find DSI Studio Cloud. Make sure you find the one under your account, not the original repository under the Frankier, because you can only run GitHub Action on your repositories. Now click on the Actions tab. You may need to enable it for the first time to run GitHub Action. The setup is now complete. That is all we need to do to set up the DSI Studio Cloud environment. Now we are ready to analyze the data. Under the workflows, click the workflow named DSI Studio Cloud. The Run Workflow button here allows you to trigger the workflow. The rows below are workflow records. Once a workflow is complete, you can check each of them here. Now click on Run Workflow button to bring up a menu. In this menu, there are checkboxes and input options to configure the pipeline. The first item you will need to input is the Open Neuro dataset number. The default number DS001021 points to a dataset called the NKI sample. You may review the NKI sample dataset on the Open Neuro website by searching the dataset number. The NKI sample dataset only has one scan data. We will use it here as our test sample. The next checkbox decides whether we will apply FSL's eddy and top-up correction. DSI Studio Cloud will use reverse phase encoding data to correct for susceptibility artifacts. If there is no reverse phase encoding data, only the eddy correction will be applied. Checking this option would add an hour of processing time or more. For testing, you may uncheck it for the time being. The next checkbox will rotate dWi and btable to align the ACPC line. After these pre-processing steps, there are three analysis pipelines. The first pipeline is the region analysis pipeline. In this pipeline, DSI Studio Cloud will compute the average diffusion metrics across different brain regions defined by built-in atlases listed under the option below. The default atlases include HCP-MMP and FreeSurfer-DKT. You can include multiple atlases separated by comma. The documentation has a list of supporting atlases that can be used here. In this pipeline, DSI Studio will normalize dWi data to the template space, calculate average diffusion metrics at each brain region, and output the results in a text file. The second is the connectivity matrix pipeline, which will derive connectivity matrix and network measures based the same atlases listed below. The third is the automatic fiber tracking. This pipeline will map tracts listed under the tracts of interest. You can assign multiple tracts separated by comma. DSI Studio will map each of them and compute diffusion metrics such as its diffusivity value and also shape metrics such as diameter and surface area. Once ready, click on the Run Workflow green button to trigger the analysis. Now we successfully start the analysis. After few seconds, you will see the workflow is queued and then processed. You can cancel the workflow at any time, or you can add multiple of them to the queue. To check out the details, click on the running workflow. Here it shows the flowchart of the DSI Studio Cloud pipelines. Now it is transferring data from Open Neuro to GitHub Runner. After data transfer, there is a first quality check before pre-processing steps. While the quality check is undergoing, the pre-processing will also run at the same time. The preprocessing here will include eddy, top-up, or align ACPC. If there are multiple scan data, preprocessing will run in parallel. After preprocessing, there is a second quality check. This can check if the quality issues are resolved. At the same time, the preprocessed data will go through reconstruction. The reconstruction method here includes DTI and GQI. After reconstruction, there will be 3 pipelines running in parallel. They include region analysis, connectivity matrix, and automatic fiber tracking. Region analysis will compute anisotropy and diffusivities at each brain region defined by the atlases. The analysis results will be saved as text files that can be downloaded. The connectivity matrix pipeline will use whole brain fiber tracking to derive connectivity matrices and network measures. The automatic fiber tracking will map fiber pathways. The tractometry result for each pathway will be saved as text files. All pipelines will save output data in the release section at the front page. Now we can see that the preprocessing is complete. The second quality check and reconstruction is now undergoing. We can even observe the command line output at each processing step in real time. Here, let's check the download data step in more detail by clicking on it. Inside this data download process, there are multiple steps, and we can expand each of them to check the log output. Further clicking on the first line will show the bash script called in this step. Here it shows how DSI Studio Cloud downloads Open Neuro data using Amazon Web Services. You can also check the commands and parameters that were used to call the DSI Studio program. The script can be modified to customize the pipeline. We can go back to the workflow summary by clicking on the summary button. Now let's check the quality check step. Similarly, we can check out the command used to call the DSI Studio program and also its output messages. Back to the summary, now the pipeline has finished the reconstruction step and the second quality check. Likewise, we can see the details of the reconstruction command. All the log output will be recorded for examinations. Again, back to the summary. Now the analysis is reaching the 3 analysis steps listed here. They are running in parallel. We can also check the analysis output in real time. Let's check the region analysis step. We can see that DSI Studio Cloud is busy calculating data for each region. Once complete, the results will be saved as text files and available for download. Let's go to the front page to check out the release section. There are previous workflow results from different Open Neuro datasets. Click the release link here to see the analysis output. There are results from 4 different Open Neuro datasets. The one we just got the results is DS001021, the NKI sample. On the top, there is another one from DS1378, a DTI study will much more scan data. All of the results are publicly available under the assets. You don't need an GitHub account to download them. Now let's check the output of the results. The first is QC1 text file from the quality check step before eddy and top-up. Click to download it and open it in any text editor. Here it only shows one scan dataset. There are different columns showing the information, including the image size, dWi count, and maximum B value. Most importantly, there is a quality metric called neighboring dWi correlation, also known as NDC. This value is sensitive to motions, eddy current distortion, and signal quality. Now let's check out the QC2 text file. This is the quality after eddy and top-up. We can compare it to QC1, which is before the eddy and top-up correction. As we can see here, the neighboring dWi correlation is increased from 0.83 to 0.85 after eddy correction. This confirms that the correction was successful. Let's check out the quality in a much larger study. The SCA2 DTI study. The QC1 before eddy and top-up shows an overview of the data quality. The first to check is whether the image acquisition is consistent across all scans. Sometimes there could be one or more scans showing a different image dimension or B-table. This quality check can quickly pick up questionable scans. Then, we will check the neighboring DWI correlation, the NDC values. The quality check will use an outlier detector to label scans with low NDC values. Let's check if eddy correction helps improve the quality. Click on QC2 file to see the quality after eddy correction. Here we make a side-by-side comparison. Most NDC values are increased after eddy correction. However, there are still scans labeled with outliers, likely due to uncorrectable motion artifacts. A strategy here is to drop those scans labeled with outliers after eddy correction. Now let's check the output from different analysis pipelines. Go back to the NKI sample data. There are zip files, and each of them stores the output from a different pipeline. Let's download all of them to check what the output looks like. Unzip them to different folders. In the region analysis, there is one text file. If you have multiple scans, each scan will produce one text file. We can check the text file in Excel. As you can see here, each column represents a brain region defined by the atlases. Each row stores a metric. There are anisotropy and diffusivity values for each brain region. The maximum and minimum values of the metrics at each brain region are also listed. Now let's check the connectivity matrix and network measures. There are 6 files generated here. 3 of them are based on HCP-MMP Atlas, whereas the other 3 are based on FreeSurfer DKT Atlas. The 3 files include the connectivity matrix stored in the MATLAB matrix format, and we can check it in MATLAB. The matrices include the connectivity matrix and associated information about the atlas and brain regions. The detail about the content can be found in the DSI Studio documentation. Here we can visualize the connectivity matrix for inspection. The other output includes the network measure calculated from graph analysis. They are stored in a text file, and we can check them in Excel. As shown here, there are global network measures for the entire network. At the bottom, there are nodal network measures for each brain region. Each row represents a network measure, and each column at the bottom is for each brain region. The third output is a text file for generating a connectogram. You can use it on the Circos website to generate a connectogram and visualize the network. Now let's check out the automatic fiber tracking results. These 2 files are for the arcuate, and the next 2 are for the forceps major. The first file is a text file storing the metrics. At the top are the shape analysis metrics, and below are the diffusion metric. The other output files ended with tt.gz are tractogram, and we can view them using the DSI Studio program. To show the tractogram, we need the fib file, which is stored in a different zip file. Open the fib file in DSI Studio's Step T3 Fiber Tracking. DSI Studio will show the image space, and then we can load the tt.gz file to view the tractogram. Select both the 2 tractogram files here, one for the arcuate, another one for the forceps major. We can inspect the tractogram in more detail from different views in DSI Studio. Similarly, we can check the forceps major. Finally, there are records of the entire processing pipeline summarized as a report on the right. This will help complete the method section of a paper. We have checked all pipelines in DSI Studio Cloud. In the future versions, there could be more pipelines added to broaden the scope. We expect that the future of brain imaging analysis will become more widely available and portable for everyone to use it. The practice will also encourage open and reproducible science, with a hope to improve our understanding of brain structure and functions. Thank you for your attention.